Hello everyone, I welcome all of you into the enrichment classes day 2 for chemistry. Today we will discuss a very special topic known as tautomerism. Now tautomerism is basically a phenomena in which two structural isomers undergoes dynamic equilibrium between themselves, and normally this happens in liquid phase. Now let us see the details of it. A very common question that is being asked is that what is the difference between the resonance and the tautomerism? Because in the resonance also we can see the transfer of electrons, and here also we can see the same, but the basic difference is the resonating structures may or may not be isolable, but here the isomers that you see which are in rapid equilibrium with each other are, it is possible to isolate them in the pure state. So that is the main difference between the resonance and the tautomerism. The most well-known form of tautomerism is known as Keto-Enol Tautomerism. Let us see how it is. If we take a keto form, like this, and this keto form, as you can see over here, the C double bond O is accompanied with a CH3 group. Let us take, these are hydrogens actually. It can be converted to enol form like this way. So this is known as Keto-Enol Tautomerism. Now let us see how it is done actually. Apart from Keto-Enol Tautomerism also, there are some other examples of tautomerism, less important compared to Keto-Enol Tautomerism of course. Those are Lactam tautomerism. Let us see how it is. This is the Lactam form, and it is getting converted into the lactim, which is N double bond C single bond O OH. There is a bond on this side. So this is lactam tautomerism. Then there is another one known as ketimide enamine tautomerism, that is CH C single bond double bond NH. It becomes C double bond C NH2. Then there is isonitroso tautomerism. This is how it looks like. CH single bond N double bond O, C double bond N single bond OH. And then the last one I would like to discuss is the acinitro tautomerism, that is CH N double bond O. It's a coordinated bond. C double bond N coordinated bond, that is OH. So this is how it looks like. So these are the examples of various type of tautomerism. Let us see a few cases which will help us to solve a few problems from the JEE mains or the NEET exams. We have chosen acetyl acetone. Acetyl acetone will look like this. CH3 C double bond O CH C double bond O CH3. I have written this hydrogen like this. It is observed that its keto form is only 20% and its enol form is 80%. That means more stable. Let us find out the reason. With the base catalyzed mechanism, if we see the OH minus, if it attacks here, this bond will come here and this bond will go here. So it will form CH3 C O minus, here there will be a double bond, CH C double bond O CH3. And of course, as we know from water, this will form OH. So let us rewrite CH3 C OH double bond CH C double bond O CH3. So if we try to write down the name of it, it will be 4 hydroxy pent 3 in 2 on. Check carefully onto this side. The hydrogen and oxygen very close to each other. So this additional hydrogen bonding will take place. And not only that, 1, 2, 3, 4, 5, 6 is 6 membered ring will be formed due to this hydrogen bonding, which is exceptionally stable. That is why its enol form is much more stable, which is 80% of the equilibrium. That means the equilibrium will be mostly on this side. So that is why it is so special, and the question you can face related to this. Another case is 1,2 cyclopentadione. Here we can see the 2 C double bond O groups are almost on the same direction. So although it is a 5-membered ring, but because 2 polar groups are on the same side, so energetically they are very high. So there is no possibility to lower this energy, because this C double bond O cannot go to the opposite side because it's a cyclic molecule. They are supposed to be on the same side. So that is why it is observed that, you see, these are hydrogens, right? It is observed that by base catalyzed or acid catalyzed mechanism, this happens. The bond is broken down and the double bond is opened up. So as a result of it, if I rewrite, it will be like, there is a double bond, hydrogen I am not writing, single bond O minus double bond O. There is a hydrogen of course, but which I am not writing. I think it is understandable. Now this O minus can obviously take the H plus from the aqueous medium, and ultimately it forms this one, which is OH, and then there is a double bond O. Now this enol form becomes stable. Why so? Number one, the 2 polar groups, same polar groups are not there anymore. And number 2 is that the possibility of this hydrogen bonding, intramolecular hydrogen bond, which makes this compound very stable. It is observed to be 100% almost. So the enol form is almost 100% over here. In case of biacetyl, we can see the biacetyl will look like this: CH3, C double bond O, C double bond O, CH3. So here also there are 2 polar groups like the previous case, delta plus, delta minus, delta plus and delta minus. But since they are on 2 opposite directions, this is exceptionally stable. It is found to be almost 100%. So although there is a chance that if I rewrite this CH2 and as hydrogen, and if you want to show the Keto-Enol Tautomerism like this, it can form, it will be like CH2 double bond C OH C double bond O CH3. But you see, this C double bond O and OH is on two opposite sides. So if they want to form the hydrogen bond, there is only one option, that it will be like CH2 OH, and this part rotates. So it forms C double bond O CH3. Then only the hydrogen bonding is possible. Then only. But the rotation of this is found to be a comparatively difficult process. So they rather would like to be stable in this condition only, not on this condition. So here, instead of enol form, keto form is much more stable. So different kind of compounds will show this kind of different type of their attitudes towards the keto-enol tautomerism. In some cases, the keto form being stable, in some cases the enol form will be more stable, and because of these electronic reasons as well as the stability reasons. Let us take another example. We have taken this keto form. If I want to rewrite this will be C double bond O, CH single bond H, just to make it much more easier for keto-enol tautomerism. And now, if this bond goes here, this will be here by acid or base catalyzed, whatever. And we should be able to write OH, CH, this one. After the formation of this, you see this double bond. Carefully, if you see, this double bond can come here. To maintain the valency, this double bond can go here. Now this one can go here. Here means in between these two. To maintain, this one can go here. This one can come here. So all the double bonds onto these two phenyl rings will be in conjugation. In conjugation. In which case? In enol form. So as you know, this is called extensive pi conjugation. Pi conjugation means what? It's a double bond is rotating around. That means the electrons are getting circulated throughout the compound. That means it is obviously more stable. So in this case, the enol form will be much more stable compared to the keto form because of this extensive stabilization. We have taken another example of 4,4,4-trifluoro-2-butanone. So you can see on this position, the 4 position, there are 3 fluorines. So this is obviously keto form. Let us see which form will be more stable, the keto or the enol form. So you see this hydrogen. If this hydrogen come here, if this hydrogen can come here, then this double bond can rotate. So in that case, we should be able to write this same molecule once again like this. There are 2 fluorines here. 1 fluorine will be here. Then there is CH. Then what I can do is, there will be double bond C here. Double bond C. Now, instead of writing this C double bond O on this side, if I write it on this side, and if I write CH3 over here, then with this O, see, it was C double bond O, but now it should be OH, because this hydrogen will be shifted here. That means this hydrogen is here. It is now enol form. You can see this in and all. Between this fluorine and hydrogen, there will be the formation of a very, very strong hydrogen bonding. So that is why I have intentionally drawn this OH on this side. So since due to the formation of this intramolecular hydrogen bond, this enol form will be more stable. So after understanding the concept of tautomerism and going through the various cases of tautomerism, so here are 2 standard questions given. You are asked to solve it and write down the answers under this video in the comment section only, so that I can able to check this, and in case of any problem, obviously you can raise the question over there.